So right now we know how to solve a systems of equations using algebra or by graphing. And that's one method that or two methods really, that we want to have. But what happens if I have in my systems of equations, say, more than two equations? Well, the algebra behind that can get a little messy, and so we might want an alternative or another way for us to be able to solve a systems of equations when I have multiple equations. And that's what we're going to look at now. If we take this system over here, notice that this is a system of three equations with three variables. We can rewrite this system using what we call an augmented matrix and set up a matrices. Now, a matrices is really just a series of rows and columns that represent specific parts of my original system. These two statements here, the system, the algebraic system you see on the left and the augmented matrix you see here on the right, are equivalent statements. Now, how do I get these two statements? Well, the augmented matrix, let's talk about that for just a second. I'm going to put a vertical bar right here. The reason I did that is because this portion over here, these three rows and columns, and really just the three columns that you see here on the left of my bar, represent the coefficients for each of these variables in my system. Now, the columns are going to come like this. So the first column represents the first variable in my system, which is x's. The second column would be the y variables, and the third column would be the z variables. And each of the columns represent the coefficient for that variable from the system. So here in this first row is equivalent to this first equation here in my system. And in that first equation, the x variable has a coefficient of 1, which is what we write over here in the augmented matrix. The y variable has a coefficient of -2, which is what we write in the augmented matrix. And the z variable has a coefficient of 3, +3, which is what we write over here in the augmented matrix. Now, when we take the variable portion of a matrix and we include it with this last column here, which is kind of what I call the answer column, the combination of these things, the variable portion along with this answer column, creates what we call an augmented matrix. Now notice that this 7 comes from this 7 from the equation. So when I smash these two things together, I get this augmented matrix. And these two are equivalent statements. Now what can I do with this matrix, with this matrices? Well, we're going to learn that we can perform a series of operations on this augmented matrix to turn it into a matrix that looks something like this. This is a unique matrices where I have ones along the diagonal and I have zeros above and below that diagonal. It's a special matrix called the solution matrix, and once I turn the original augmented matrix up here into this solution form down here, it creates this column, which is the last column again, and it tells me then what is the answer for x, y, and z. So by doing these operations on the matrices and putting it in this form, it all ends up telling me what the solutions are for my system. Now we're going to do this, find this solution matrix using the Gauss-Jordan elimination method. It's just a special type of, special way of reducing our matrices so that it's put into this form. I said that in order for us to get it into that solution matrices, we're going to be performing a series of operations. So there's three operations that we're going to be performing. The first one that we want to look at is just a row swap. In other words, if this is the matrices that I'm looking at, I can switch the first row with the third row to create a new matrices. Now, I am going to do that. I am going to swap row 1 with row 3, and I'm going to get in the habit of writing down the operation underneath my matrices that I'm looking at. That is going to create a new matrices that looks like this. My matrices is going to have a bracket like this, Now the first row of this matrix that we're writing is going to be the row number 3. So it would be -3, 2, -2, -10. The second row stays the same, so that's still 2, 1, 1, 4. And the third row in my matrices is going to be what this was up here, 1, -2, 3, and 7. This is now the new matrix after I changed rows 1 and row 3. So it's just a row swap. The second type of operation that we're going to look at is maybe I want to multiply a particular row by a constant or by 1 over that constant. Okay, and there's a reason we might want to do that, but that's what our operation is going to be in this one. So let's say that I want to multiply -4 times row 3, giving me a new row 3. And that's what my notation says down here. I'm going to multiply the current matrix by -4, and it's going to end up giving me a new matrix, a new row 3 in my new matrix. So when I rewrite this, the first two rows are going to stay the same. So I have a 1, -2, 3, 7, 2, 1, 1, 4. Now it's the last row, row number 3, that I'm going to multiply every individual number that's in that row by -4. So -4 times a -3 is a positive 12. -4 times a positive 2 is a -8. -4 times a -2 is a positive 8. And -4 times a -10 is simply 40. And for reasons that you'll see soon, we will want to do this, but that's what we're doing. So now we can multiply a row by a constant. The last operation that we're going to look at is if I want to add a multiple of a row to another. What does it mean when I want to do that? If I want to add a multiple of a row to another, let's say, for example, I want to multiply -4 times row 1 this time, add it to row 3, and that's going to give me a brand new row 3. Now, this is a pretty important step for us because we will be using this concept a lot. So I'm going to multiply -4 times row 1, add it to row 3, and I'm going to get a brand new row 3. So what does that mean? Well, rows 1 and 2 are not going to change. So I'm just going to rewrite them as they are. 1, -2, 3, 7, 2, 1, 1, 4. Row 3 is the row that I am going to be changing. Now how do I get it? Well, I'm going to multiply -4 times row 1 and add that to -3. So in other words, it's going to look like -4 times 1 plus a -3, and that's going to give me -4 plus a -3 is going to give me 7, and that's what goes right here. Now let's do that again with the next position. So I'm going to multiply -4 times -2, and I'm going to add that to 2, and that's going to give me 8 plus 2 would be 10. So that's going to go down here in this position. We do it again. -4 times 3, and I add that to -2. It's going to give me 12, -12 and -2 would be -14, which would go here. And then finally we have 7, so then the last one would look like -4 times 7 plus a -10, so that would be -28, so -38. Okay, so you can see that this final operation says that I'm going to multiply one row, add it to another row, and it gives me an entirely new row over here. Now all of these 3 operations and many others can be done in our calculator. And we are going to use our calculator to be able to do this because it just helps us out with kind of what I call the grunt work, you know, just basic multiplying and adding, whether I'm doing it with fractions or whatever. It kind of helps keep it straighter. But we'll talk about how we can do that on our calculators in the next video. So these are the three operations that we're looking at. We're going to change the rows, interchange them. We can multiply or to change a single row, or I can multiply and add a row to get a totally new row. And that's what we're going to do in the next example.